All right, so today's topic is Network of Things, but the whole slides are actually adapted from NIST Special Publication 800-183, Network of Things. So I recommend all of you to read it, but you can think this lecture or the slides as the best of version of that documentation. So I kind of highlighted important parts, then we can see how we should actually look at Internet of Things or also Network of Things. So let's start again with the picture from this document and look at how NIST actually sees the problem. So NIST prefers to call it Network of Things because most of the time these devices are not connected to the internet. Okay, so Network of Things are a better, I mean, the name is not that nice anyway, Internet of Things or Network of Things, but anyway, Network of Things is a broader term. So they look at the primitives and they try to explain and determine what are the important parts or what can go wrong. So we have sensors. That is the main idea. And we can group them and call them clusters. Okay. And these sensors actually measure something. It can be humidity if you are dealing with agriculture. It can be temperature. And these sensors might be spread on the field. It can be in the farm. It can be under the water. So they are sending information. So they're actually using a communication channel. So one problem is this. So these devices are not that capable. A second thing is that which communication channel would be better for these devices? Because if they're running on battery, we would prefer to have a communication way that consumes less energy. So these sends data to some devices which we call aggregators. And these aggregators actually communicate with each other. And then actually there is an external utility maybe here, which performs operations. Here is an example. For instance, if some values are larger than something, it says set wing flaps to 10 degrees. So in factories, in dams and so on, this kind of automatic systems are used. So external utility can also be a laptop here, perform computations and give commands to aggregators and so on. So this is the kind of a big picture how things work. So we should actually talk about what the sensor is, what can go wrong, or what the cluster is, and so on and so forth. So let's start with an introduction. From agriculture to manufacturing to smart homes to healthcare and beyond, there is value in having numerous sensory devices connected to larger infrastructures. Also, this is currently a trend in smart homes. Almost every device connected to a main hub, and you control it with your mobile phone, etc. This technology advance acknowledges the reality that human society is moving towards smarter and smarter systems. The rapid advances in computer science, software engineering, systems engineering, networking, sensing, communication, and artificial intelligence are converging. The tethering factor here is data. So there is no formal, analytic, or even descriptive set of the building blocks that govern the operation, trustworthiness, and life cycle of Internet of Things. So this is one of the main problems. So the technology improves really fast, but we don't have maybe any regulations, any definition, etc. A composability model and vocabulary that defines principles common to most, if not all, network of things is needed to address the question, what is the science, if any, underlying IoT? So this is why I'm preferring this document for this. NIST Special Publication Network of Things offers an underlying and foundational science to IoT based on a belief that IoT involves sensing, computing, communication, and actuation. Okay. Because no simple, actionable, and universally accepted definition for IoT exists, the model and vocabulary proposed here reveals underlying foundations of the IoT. By here, of course, I'm referring to NIST documentation. In other words, they expose the ingredients that can express how the IoT behaves without defining IoT. This offers insights into issues specific to trust. We consider IoT to be one type of network of things, and network of things to be one type of a distributed system. This is important because there's already an area called distributed systems or sensor networks and so on and so forth. So these are kind of converging in many areas. So the NIST defines the primitives of network of things as follows: sensors, aggregators, communication channel, external utility, shortened as e-utility, and the decision trigger. Rarely there may be some network of things that do not contain all of these, right? Maybe you are dealing with small systems, maybe some of them are missing, but generally we have all of them. So our aim is to look at all of these primitives, try to define them and see what kind of properties they have and how we should look at the problems. So we start with the first primitive, sensor. A sensor is an electronic utility that measures physical properties such as temperature, acceleration, weight, sound, location, presence, identity, etc. So don't always think that these sensors are just independent devices scattered around the field. We also have sensors in our smart cars, in maybe the wheels or other parts of the car which communicate with each other. Okay, so if one tire of the car detects something, for instance, a block or a small thing, so it actually measures this and sends this data to other parts of the car, which actually behaves in that respect. So this is a broad topic, anything smart actually is kind of can be think like this. So, but important thing is we have sensors, and the number of sensors and number of data we measure actually increases all the time. Even smartwatches come with many different sensors now that we didn't have before. All sensors employ mechanical, electrical, chemical, optical, or other effects at an interface to a controlled process or open environment. Basic properties, assumptions, recommendations, and general statements about sensors include. So these are kind of my best of part from this document, okay? So instead of for you to read all of these pages, I kind of summarized it for you. Sensors are physical. Some may have an internet access capability. So if it is if it is less capable, of course, it cannot connect to internet, right? But sometimes if you have a better equipment, let's say, you may have internet access. Sensor output is data, and data is the new oil, so it is really expensive and, it has value. A sensor may also transmit device identification information, such as via radio frequency identification. This is important because sometimes you have to check the ID of a device, because a malicious people may add a different sensor there and may give you poison data. Okay. Sensors may have an identity or have the identity of the thing to which they are attached. Sensors may have little or no software functionality and computing power. More advanced sensors may have software functionality and computing power. So sensors may be heterogeneous from different manufacturers and collect data with varying levels of data integrity. This is important because even although you buy all of your sensors identical, years later you have to renew them or add more. And most probably the sensors you bought won't be in the market anymore, right? So you'll be putting different sensors, so the system will be heterogeneous. Sensors may be associated with fixed geographic locations, or they can be mobile. Sensors may provide surveillance, cameras, and microphones are sensors. So these are important. Actually, let me go back to the previous one. Don't always think that sensors are fixed at a specific location. They may be mobile, but also, since cameras or microphones are more capable devices, people don't think that they are sensors, but actually, in this case, we look at them also as sensors because they provide surveillance. Sensors may have an owner who will have control of the data their sensors collect, who is allowed to access it and when. And sometimes companies may share, their data. Sensors will have pedigree, geographic locations of origin and manufacturers. Pedigree may be unknown and suspect. Sensors may be cheap, disposable, and susceptible to wear out over time. So this is one of the problems when you try to build something a lot. You want to do it as cheap as possible. And once you do it as cheap as possible, those devices are not the same or give you the same performance all the time. Okay. So manufacturing quality really applies here, There may be differentials in sensor security, safety, and reliability, for example, between consumer grade, military grade, industrial grade, etc. And actually, this sentence applies to almost any electronic device. For instance, when you buy a router, you think that this is the best, right? Because it is the most expensive on the market, but you realize that military uses something else. So industrial grade, military grade, really different than personal devices. Sensors may return no data, totally flawed data, partially flawed data, or correct and acceptable data. Sensors may fail completely or intermittently. They may lose sensitivity or calibration. So actually, this is like one of the most important things. So you cannot always rely that data is correct, right? So this is why you should be checking its reliability, if it is really working correctly. Sensors are expected to return data in certain ranges, for instance, an integer between 1 to 100 or any real number. When ranges are violated, rules may be needed on whether to turn control over to a human or machine when ignoring out-of-bounds data is inappropriate. So although this is just a basic sentence, this always happens. Actually, this applies to any software, You should be careful if you are getting values that are out of range. Sometimes people write codes in a way that they don't check this kind of stuff, and this violates many memory accesses, and actually you end up with troubles at the end. So you should be careful if your sensors are giving out of range values, because this may be a sign that they are malfunctioning. Sensors may be disposable or serviceable in terms of calibration, sensitivity, or other forms of refresh. Complex and expensive sensors may be repaired instead of replaced. Sensors may be powered in a variety of ways, including alternating current, solar, wind, battery, or passively via radio waves. Sensors may be acquired off the shelf or built to specification, but of course, generally we buy off the shelf. Sensors require data that can be event-driven, driven by manual input, command-driven, or released at predefined time. So it depends on the use case, right? Sometimes people prefer, getting data at specific intervals, especially in agriculture and so on. But sometimes it can be event-driven or can be done by manual input. So sensor may have a level of data integrity ascribed. It depends on its capacity. Sensors may have their data encrypted. So this is actually what we hope for, right? This is what we are actually trying to talk about in this lecture. So in this course, our aim is to, try to provide encryption for every communication, regardless of how small or incapable the device is. We will prefer that it has confidentiality via encryption. It has integrity, maybe with hash functions or authenticated encryption. Also, we should, have some kind of authentication. So every cryptographic protocol kind of applies here, but we need to do it on small devices. And they may be really small, like, they may have maybe a few bytes of memory and so on. Sensors should have the capability to be authenticated as genuine, as I just mentioned. Sensor data may be sent and communicated to multiple network of things. A sensor may have multiple recipients of its data. Sensor data may be leased to one or more network of things. So in the future, this will be actually more common, because companies will be selling data to each other at the end of the day. The frequency with sensors release data impacts the data's currency and relevance. Sensors may return valid but stale data. Sensor data may be at rest for long periods of time. Yes, this is important. If you actually get more data or more data in a time period, you can check its correctness, relevance, but you will be consuming more energy in this case. So you should try to get a sweet spot for that. A sensor's precision may determine how much information is provided. Uncertainty of sensors data should be considered. Sensors may transmit data about the health of a system, such as is done in prognostics and health management. It will be nice if you know before the sensor is broken, right? So this is why we prefer to have some kind of health checks. For instance, in computer devices, we generally have, like in SSDs, in an ideal world, it should tell you that it is going to be broken in a few weeks, so you should replace it and back up your data, right? So in this model, we don't classify humans as sensors. Of course, this is NIST decision, and I totally agree. In some of the Internet of Things definitions, they also classify humans as sensors, okay? But I prefer not to do that. This is important. Humans are classified as an external utility. They can still act in a sensor-like role by manually feeding data into a network of things workflow and data flow, but they shouldn't be considered as sensors. Humans can influence sensor performance through failure to follow policy, sensor misplacements, etc., or their positive analogs. Humans are potential contributors to sensor failure. So this is really important because, these are electronic devices, so you should be checking them from time to time. Putting it on the field and, leave it there for years, most probably it will start giving wrong results. So humans can make a mistake by not following the policy, or misplacing the sensors, or analyzing the data in a wrong way. So security is a concern for sensors if they or their data is tampered with, stolen, deleted, dropped, or transmitted insecurely, so it can be accessed by unauthorized parties. Building security into specific sensors may or may not be necessary based on the overall system design. If the attacker cannot access the sensor, and the data communication, then maybe you would be okay to not have encryption. So actually, this was the idea in the industry before. So in most of the factories, devices communicate with each other without any encryption. But nowadays, all of those factories are connected to internet, so disasters start to happen. So you should be looking at your design, but also you should be thinking about ahead, maybe in the future. I mean, maybe currently you don't need encryption, but maybe in the future you will have. And of course, reliability is a concern for sensors.